Okay, so we're still looking at LaChateliers principle, and we're going to look at how changes in temperature affect our reactions. Okay, so the effect of temperature on equilibrium has to do with the heat of reaction. Okay, this was a couple of units ago. Recall that for an endothermic reaction, heat is absorbed, and the value of delta H is positive. For an endothermic reaction, we can picture heat as being a reactant, and this is pretty important, okay, because you're going to treat heat just like a reactant or a product, okay, and so here you have heat plus A yields B. For an exothermic reaction, the situation is just the opposite. Heat is released, okay, and so heat, therefore, is a product. Now, if we picture heat, let's pick another color. Let's do yellow. If we picture heat as a reactant or product, we can apply LaChateliers principle just like we did for our discussion on raising or lowering concentration. For instance, if we raise the temperature on an endothermic reaction, it is essentially like adding more reactant to the system, and therefore, by LaChateliers principle, the equilibrium will shift to the right. Conversely, lowering the temperature on an endothermic reaction will shift the equilibrium to the left. So this section, it might be very useful for you to treat heat and the values and actually write them into the equations. So let's look at an example. Oh, we got one more little sample. For an exothermic reaction, heat is produced, or the product. Therefore, increasing the temperature will shift the equilibrium to the left, while decreasing it will shift to the right. Okay, so let's consider this reaction here. We have an exothermic reaction, and so we would think of this on the product side, okay, because heat is being released. Okay, so what happens when we increase the temperature? Okay, so think of this as a product, and if it helps for you to rewrite that entire reaction, do it. But if we increase the product, we're going to push the reaction to the left. Okay, so since the reaction is exothermic, okay, an increase in temp adds stress to the product side. Equilibrium will shift towards the reactants. Reverse reaction is favored. And writing all that, I'm just trying to give you an arsenal of things that you can, different phrases that you can use. Okay, so same problem, still exothermic, but we're decreasing the temperature, so we're taking some of that out. So since this is exothermic, and I'm abbreviating a lot here just to save time. Okay, reaction will shift forward. Because stress is on taking products away. Forward reaction is favored. Okay. So last but not least, introduction of a catalyst. We're just going to highlight a few things here. Okay, so catalysts decrease the activation energy. So think back in kinetics. Catalysts lower the hill, okay, the hill that it takes for reactants to convert to products. But they decrease the activation energy of both the forward and the reverse reaction equally. So equilibrium constants aren't changed if you add a catalyst. The only thing they change, the only thing that can change an equilibrium constant is a change in temperature. The position of equilibrium is not changed if you add a catalyst. And the explanation is that a catalyst speeds up both the forward and the back reactions by exactly the same amount. Dynamic equilibrium is established when the rates of the forward and the back reactions become equal. If a catalyst speeds up both reactions to the same extent, then they will remain equal without any need for shift in the position. So now we're going to practice some of these reasonings on a few different problems. I am going to stop the video here in a minute, and you're going to have a chance to go through that. But I wanted to kind of show you what to do. So 17.9 and 17.10 and 17.11 we're going to all do here in a minute.